be here joining the last part of the session. My name is John Fan Hu. I'm the host for the sessions this morning. Okay. Such a beautiful weather to be here is quite a lovely things in my life, right? You can't agree more if you participate in the Teachers' Day ceremony in a Confucius temple, right? And then enjoying the beef soup, right? People in Taiwan often say the best part, the best wine at the bottom of the jars always tastes best. So let's join the last three sessions in the morning. Let's welcome the first presenter, Professor Houpt. Thank
you. Well, good morning, everybody, and thank you for your stamina and making it through this far. Yesterday, I talked some about the general systems factorial methodology. Today, I really want to focus in on using the capacity coefficient, a measure introduced, as well as Dan Little's introduced some of the work on capacity coefficient, in particular examining configural superiority effects. All right. So what is configural superiority? There are a few different definitions I looked up. The first definition was from Jim Pomerantz on the Configuwiki, which I'll highlight in a moment. There's an improvement in discrimination performance resulting from the addition of information with context. So if some of you are familiar with Pomerantz's work, he's done a lot of stuff with these arrows and bars, and depending on how you orient them, you get different configurations. Your performance can vary quite widely. Another one, I think this actually might have been contributed to by Pomerantz as well in the Oxford Dictionary of Psychology. When a configuration yields performance better than parts in isolation. So in particular, I wanted to highlight that here it's talking about adding information with context. I've got this one. Yeah, this is mine. Anyway, so okay. And then also another part that's not in either of these definitions, but I think is also important for configural superiority, that it's really a particular configuration that leads to superior performance. Okay, so I wanted to highlight Configuwiki in particular. I promised Jim and also highlight the configural processing consortium. So I'm stealing away top and time from myself to direct you, hoping that those in the room are particularly interested in configurality. This configural.org, which is the website for this conference, Configural Processing Consortium. And this is usually tagged along with the Psychonomic Society meeting. There's excellent presenters there with some of the big names, all the big names really, many big names in configural perception. Will be there. Again, configural.org is the website. Ami Yale's information is on his participation. If you email him, you can ask about talks and general information like that. So, quick highlight of that. The other thing here is this Configuwiki link here on the page. So this is a site that was set up in conjunction with the conference. Oops. Well, I guess I won't actually show it to you. To kind of be a discussion forum for some of these issues that come up. So questions like what exactly makes a feature, and is it even worthwhile to define a feature? Having those kinds of discussions on it. It's been a little inactive for a bit, but hopefully by highlighting, we can get a little more work on it again. Okay, so that's what Pomerantz contributed to this definition is on that Configuwiki. Back to the content. 1 second. Okay. So a couple of
Sorry, just one other thing is, I think the kind of dialogue that we've gotten going here is kind of the essence and spirit of the kind of dialogue we've gotten going here is really the essence and spirit of CPC, where we bring together the modelers and the non-modelers and establish common language and interactions and things. So very much in the spirit of I think of conference here.
All right, so definitely check out the website. It's a great conference. Okay. A few superiority effects. There are others, but these are ones that show up all over the place in the literature. This is a very small selection of the face literature really talk about configural superiority effects. One example of a configural superiority effect is the idea that when you've got a face in its canonical configuration, if you perform better on parts of the face, here when it's in its configuration, than you do with either of those parts alone. So that speaks to this first definition. Configuration parts yield better performance than parts in isolation, as well as superior performance when you have canonical configuration compared to a non-standard configuration. So you wouldn't naturalistically see faces looking like this. That would be pretty scary. So you'd expect configural superiority effects that can refer to superiority of this over each of these alone, as well as this related to this. Another popular configural superiority effect is the word superiority effect. The idea being that when you see letters in a word, you have better performance than letters in isolation, like this, or letters in sort of non-canonical configuration, so non-word letter sequences. Again, this is a small selection of papers on word superiority effect, which shows up quite a bit. Another one, so all other sorts of configural superiority effects show up. This is again a small selection of it. This one that I'll be talking about is based on an experiment designed by Jim Pomerantz, looking at how you can get the simplest possible configurations and trying to study the nature of configural perception these baselines do. So with orientation configuration, using that as a feature relative to, if you move each of these pieces by themselves, you get superiority effects, but you also have orientation cues. Okay. So to be able to look across these different configurations, be able to compare things like misaligned faces to faces, as well as talk about the degree of configural superiority when we're, for instance, talking about faces or talking about words. We need to use a common baseline to measure each of these things. So if you're here yesterday, it should be no surprise that the baseline I'm going to use is this USIP model. So again, the assumptions of that, as a reminder, is unlimited capacity, no change due to increased workload. So as I give you more things to deal with in this baseline model, it doesn't change what's happening on each individual part. Likewise, independent, so there's no crosstalk between the two sources of information. Again, this is a baseline, not what we think is going on in configural perception. And then finally, the parallel, simultaneous processing of all of the sources of information. So this gives us a baseline assumption to compare performance against. The idea would be that configural superiority should be better than this baseline. Or if you have configural inferiority effects or anti-configurality, you might find worse than this. Okay. So the capacity coefficient, I introduced it sort of at this same level of depth yesterday, but I'll quickly scan through again. You've got an exhaustive condition, so if I tell you, for instance, only say yes if both the top half and the bottom half of the face belong to the character John, then you need to check both top and bottom half of the face. So it's an exhaustive task. You have to check both parts. The idea then for you to have completed processing on the two parts together, you have to be finished on both parts together. So using the assumptions of that, use the baseline model, we can just set up this equation. We do that log transform to both sides. That gives us the sum here, which I like for the statistics, but also has some physical interpretation in terms of work. And we get this baseline prediction of the use of the model. Take the same steps doing you haven't finished the face yet, so in or task they I only care if either the top half or the bottom half belongs to John. The or task, so I haven't finished yet. I haven't finished the top half or I haven't finished the bottom half. Again, log transform between the magic functions baseline. All right, so I went through that pretty quick, and I worked through examples in a little more detail, showing how I've actually used this. Don't expect you to necessarily see this and get all of its meaning. At this point, the basic idea is that we're comparing in this capacity coefficient. We compare what happens when you do everything together with each part in isolation. And we can talk about that in terms of an OR task, an AND task, single target self-terminating task I mentioned the other day, yesterday, where you might have distracting information. This might fit for that first definition from Pomerantz, and you compare what happens with otherwise uninformative context to something alone, or XOR tasks, so you can, whatever rule you come up with, you can basically derive this baseline. And it also generalizes to a larger number of subprocesses. So the faces and the dots that I talked to you about have two pieces that I'm manipulating, top half and bottom half, or left and right dot. The words, they have 4-letter words, right? 4. So each of those individual letters or characters in the non-word conditions just goes into the equation here. So first letter, second letter, third letter. Okay. So specific to the dots, the idea then, we set up this experiment so that we're going to be measuring each of the parts in isolation to see how long it takes you to respond to those. And then measure performance when you have the parts in their configuration. And we're going to compare configuration performance to these using this USEP baseline. So if this one was happening, your performance here plus your performance here using this cumulative hazard measure could equal your performance on either of these two. So then we just measure the response times for those individually and we do those comparisons. So that's the general idea. But specific to this task, they're given a reference point, and I just ask if the dot that comes after the mask is in the same location as the reference point or not. So we can have these single dot trials where it's just a dot, mask, and then here. It's either going to be in the same location, in which case you'd say no, or a different location, in which case you'd say yes. We do that for left and right dots, basically to balance out the way we move the dots over here. And then over here we've got our configural condition where we've added an additional source of information when we move the dots. So we move these two dots in such a way that there's now an orientation cue in stimulus. But then we also have this condition where we've got redundant targets. So both of these dots are in different locations from their reference, but I haven't added the configural cue of orientation. So I can compare what happens when I use this capacity coefficient for this configural condition with the orientation cue to the baseline. So that gives me one comparison. And I can compare this to the baseline. And now that I've compared each of these to their baseline, I can compare them to each other. So in particular, I can use the capacity coefficient. Because this one moved different than this one, I can still equate the conditions. So I don't get a situation where someone might argue, well, maybe it's just easier or harder, I guess, to detect a dot moving up. I'm controlled by that for using this baseline. This is the slide I've been telling people for 2 days I'm going to fix and I never fix. So I'll walk you through it in a little more detail. This CZ here on the y-axis is a z-score summary statistic of the capacity coefficient function. And the rest of the data slides I'll actually show you the full function. So what we have here, we've got the blue up here on top is the configural condition, and the z-score for the configuration, and then this is the group level variability. I think it's 95% confidence interval. So we've got configural condition, we're comparing it to the control condition, so that's when we don't have the orientation change. We see, just focusing on this side, this middle line condition, it's quite a bit better when you have the orientation change. However, the other thing to point out, for this z-score that's 0 represents that null hypothesis of the USIP baseline. So everything here at the group level is below that 0 baseline, which means we're actually performing worse with two parts together, even when I give you the orientation cue, than you do with either part alone. But when I do have the orientation cue, it's much better, much less worse. This is pretty low performance down here without the configuration cue. The other condition we added in here is we just connected lines between these two to really push that configuration, and then also with the orientation measure, and more information about the orientation when you connect the whole thing with a line. That really didn't change the capacity very much. As a note, there was a fair amount of variation across individuals. There were some people, when we looked at their individual capacities, z-scores, that were supercapacitor above the baseline significantly. We just had enough of that below that the group level dropped down below. So that's what it looks like in the dots condition. I think I should have plenty of time, so I might stop and see if anybody has any questions about that setup or the use of the capacity coefficient in that design. Yeah.
So when you compare the single target trials, I assume that's targets. So in the single target trials compared to the case where you had the double outside orientation, I presume those single target trials also had the orientation component there. It's just you only saw one of them.
Yeah, so it's an interesting question. The extent to which there is an orientation cue here. So these single dots would be basically, if I just block this out and block this out. So it's exactly the same left-hand information. But this one, it's a kind of strong type of configurality. There's really no such thing as orientation. I mean, you can talk about it related to the frame of the monitor or things like that. But it's certainly, even in those cases, it's a much weaker kind of orientation when you're looking at these two relative to each other. So this part is the same as this part, but I would say there's no orientation there, at least not the same kind of orientation that's here, because there isn't something relative to it. So there isn't a configuration. Okay, well hopefully as I move through more of these examples, it'll become even more clear and you can start to form questions to ask me. This next task is looking at the word superiority effect. So just focusing on this top line, we've got set up the experiment, we've got the target word of care, and then we set up distractors that are single letter morphs in each position. So care versus bear, is that C versus B distinction. Care versus cure, the A versus U distinction. Care versus K is an RB distinction. So the idea is that when you're doing this task, if you're going to correctly identify care, you have to exhaustively check each of these letters. You have to make sure it's a C and not a B, an A and not a U, etc. So that gives us our actual performance of the configuration, and then we go into separate single character blocks where now they just have to discriminate a C from a B, and an A from a U, and an R from a B. And we use our response times for each of these characters to estimate that performance, assuming the baseline lucid model. And then we measure the response times over here to get their true performance of the configuration. We can compare what happens here to what happens with the predicted model based on that performance. So that's for the word condition. We also have pronounceable non-words, consonant sequences. We took the consonant sequences and flipped them upside down. And then we took characters that were relatively simple but unfamiliar to our participants. And basically ran the exact same setup on each of those. Now again, I want to highlight the advantage of the capacity coefficient is I can compare performance here to here. And that's performance on the configuration. So all of our participants, you can imagine, were pretty miserable at this distinction. After a while, they definitely got up to high levels of accuracy, but they were incredibly slow compared to the familiar character sequences. But even despite that slowness, if I get higher capacity here than here, it means they're better with the configuration. So it could be that the configuration drives difference in performance beyond just the fact that every math is unfamiliar characters. And the capacity coefficient allows me to make that comparison because I've controlled for the difficulty of the individual characters by using this model baseline. So this is what I promised you where we actually see the capacity coefficient function across time. So focusing here at first, these lighter gray lines, those are individual participants, and then this thicker blue line gives you the function across time. So average functions across time for the group to kind of give you an overall impression. And really, for the most part, everybody was above 1. There's some people's functions that go below 1 for a bit. I think I put the statistics on there. But certainly at the group level, it was supercapacity, and most, if not all, of the individuals were supercapacity reports. So better with the configuration, standard word superiority effect, better with the configuration in a word than they were with each of the individual parts alone. And that comparison then is done based on the model. Likewise, we had very similar group level performance with the pronounceable non-words. So this is a pseudo word superiority effect, something that shows in literature as well. It was a little bit less than this word level. The distinction between these two depended a bit on the specifics of the test design. But they both were supercapacity, not quite a supercapacity here. When we switch to the random letters now, we drop down And this group level performance tends to be below 1 for most of the time. Let's see. So I think for the group level was not significantly different from 0. So it looks roughly like that on the capacity independent parallel baseline level. Then when we push it even further, when we flip it upside down, so sure we expect the individual characters to be harder when we flip them upside down, but even relative to that baseline, their configural performance was much worse. Upside down, random constant sequence. And then much, much worse with the unfamiliar characters. So the capacity coefficient allows us to compare across these. I can check standard word and pseudo word superiority effects over letters alone, as well as compare words to random, so you're definitely better than words and words to upside down, etc. Good on that? Any questions on the word superiority effects then? We're happy to answer questions at the end too.
So why do you think the last one, the upside down capacity actually get better than the
So I think it has to do that we're familiar with, participants were familiar with the individual characters. So even though it's a non-canonical orientation for them, I think they're familiar enough with them, so it's a little easier to distinguish them than it is these. Again, their accuracy was still quite high on this one. It just took them a lot longer to do. So that's my guess at why it's better. We actually, part of the reason we ran this condition is on our pilot participants. We had I think it was only 1 or 2 pilot participants. We had super capacity on all of these. So we kept pushing, trying to make it harder and harder, trying to find something that was limited capacity. But luckily, when we switched to our general population, we followed a little bit more expected. Strange pilot participant was just so good at the characters.
Yeah, it might be kind of interesting to run a slightly different condition where you have might be interesting to run a side condition where you have a forward port instead, and see, for example, that difference might be primarily because of the real letters, even though they're upside down, there might be some verbal coding. Have that possibility for the commentary.
Yeah, that certainly could be. So, there's a chance, I guess, that we could name these characters. So if I had my participants doing it for a while, I could give them the names of these characters. And that might improve performance, but even still with this, I know that's RLHF, even when it's upside down, so that verbal encoding might allow some advantage over those individuals. And I think that, that completed implication will report what we do.
Have you tried using the word
No, that'd be a very interesting thing to do though. So I think, my guess would be that it would be, so it's this kind of change. So if the scale of change were the same, we might expect it to drop down. If it dropped down on that scale, it might drop down a little more on the rather than super. But I didn't try the condition. I think it'd be very interesting to try it out. Okay, so no surprise, the next thing I'm going to talk about is faces. Same kind of idea. We want to look at our canonical configuration and measure the baseline performance with each of the pieces of information that are there, and then compare that to the face and its canonical configuration as well as into its misaligned configuration. And get a capacity coefficient measure for each of those. So we can talk about capacity for the canonical configuration relative to its part. We can also talk about the capacity coefficient for this one compared to this one. So again, I think it would be kind of a stretch to argue that, but perhaps somebody could say, well, the reason you're worse over here is that this is presented just a little bit further from the center of the fovea, so it's just harder here. But because we've got this baseline condition, we can actually present that top half a little bit further to the right fixation. And so we can control for that by using this baseline performance when we want to do compare capacity across the two of these. A little bit fewer participants in this one, but the same basic idea. Well, actually, yeah. So when we have the canonical configuration, we've got super capacity at the group level, and all of the individuals actually end up being super capacity. Interestingly, even with the misaligned faces, that puts split, that's kind of a misnomer of these misaligned faces. At the group level, they were super capacity, and there were 3 or 4 of the 7 individuals that were supercapacity. So better here compared to their performance each of these individually, even though it's not the canonical configuration.
So what was the retinal spread difference between the square and the true
Not sure. It was all presented, within about 2.5 degrees, so it was not tiny but not massive. The top up, see this, the most top up top. So it's within the realm that it could possibly make a difference to make this shell shift, but it's probably not going to be huge. And then, well, I don't want to take too many wild stabs at why this might still get supercapacity. I'll leave that up to the audience members to come up with their explanation. So the align faces were definitely much higher than the split faces when we compared one to another. We did still get that supercapacity. Okay, so that's what the face to me looked like. So that's the capacity coefficient in 3 different types of configural superiority. We had the dots looking at that orientation configuration as a Q. Surprisingly, we found limited capacity with that configuration Q, but it was still better than the 2 dots together without the configuration. Next up, we had the word perception. So words, we found the standard word superiority effect and pseudo word superiority effect. And those were better both than individual characters and compared to random letter sequences and sequences of character. Finally, aligned faces, we found supercapacity, good. Pieces of face are better together than apart. And although misaligning the pieces of the face did break the configuration down a bit, it was not to the degree that it became limited capacity at the group level. Okay, so I also introduced the assessment functions yesterday. We can look at these same data sets with the assessment functions. So one thing to point out is capacity coefficients are really designed to work around high accuracy situations. But they can actually have biased performance when you have low accuracy overall, where you start to get into conditions where you have differential speed accuracy trade-offs. So if there's a different speed or accuracy focus in a whole phase condition compared to each individual parts. So if the accuracy drops down, you can get into problems where there can be potentially differential speed accuracy trade-offs. So one way of controlling for that is using these assessment functions. And the assessment functions are just the same basic idea where we take that USIP baseline model, but in addition to predicting the total response time, we also want to predict a correct versus incorrect response. So the idea of this model is we generate the response as a race between a correct process and an incorrect process. They don't necessarily have to be an independent race. So it could be something more like a Radcliffe diffusion model, where you're perfectly negative correlated between getting evidence for yes answers and no answers. So this is the basic form we're going to use to build up an assessment function. So if I want to talk about the joint probability of being correct, say on the top half of the face, it really wants me on that. Shut off. Yeah, where's the message come down? Okay, so the basic idea, if I want to be correct on the top half of the face and have responded by a particular time, so it should be less than or equal to, then we can talk about it in terms of this integral. So if you're familiar with integrals and probability theory, this should be fairly straightforward. The basic idea here is when I'm talking about the probability of being correct at a given time and being finished. Sorry, so the probability that the correct process is finished at a given time and the incorrect process has not yet finished, given that the correct one finished. And then we just want to add that up for all the possible times up to this t that I care about. So that's the basic component we're building in here. So this is the density function for the correct process. This is the conditional cumulative distribution function for the incorrect process. Okay, so then to build it all up, the basic idea is correct and it responded by a given time. Well, either we were correct on the, so for an AND case, we had to have been correct on the top half, and correct on the bottom half. So correctly identify the top half as John's face and the bottom half as John's face. So we just took that piece that I showed you in the last slide and did it for both the top and bottom half. And then take a log transform each of those to get it kind of on the same scale as the capacity functions. We'll end up with kind of a messy function looking like this, but the basic idea that it follows that same logic of the capacity function. And believe me, this is one of the simpler assessment functions. So I think I mentioned yesterday that when you look at that page in the paper, it's just a page of integrals, and again, it's most simple. So one last plug for the R package. It's all built in, so it's behind the scenes there. Okay. And there are variations on the assessment function. So just like the capacity coefficient, you can do it for OR tasks or for AND tasks. We haven't done them yet, but you could easily do them for XOR tasks or single target self-terminating tasks. Same basic logic, and he'll build them up. I'm hoping it's easy. Jim hasn't shook his head at me saying it wouldn't be easy. Relatively easy. Sorry, all this is relatively easy. We can also focus on correct and incorrect time. So right now I'm looking at the joint between correct and the response occurring by time t. I can also do the same kind of assessment function, but looking at the joint of being incorrect and responding by a given time. Likewise, I can do this fast version, we call it the paper, which is based on these conditional CDFs, so where I'm focusing on t less than or equal to a given t. Or I can also do it based on the survivor function. So this sort of corresponds to how we develop the AND capacity coefficient and the OR capacity coefficient. So we can again look at this joint both ways, and you get something kind of similar to this. There might be a mess of more terms out there, but the same basic idea. And then there's also the OR task that can vary between whether you're doing a detection task and a discrimination task. Just based on sort of how you could, the different ways you could accidentally be right in a detection task. It's a little bit different from the discrimination task. But there are all of these different versions you can say, do an OR, incorrect, fast discrimination, or an AND, correct, slow, detection. All of those versions are out there on the R package. So we can just take them and basically drop them on top of those results. So here we've got the dots data again, but now this time I'm showing you the actual capacity functions rather than just that interaction plot. So this is without lines. We're looking at the control condition and the configural condition. So where I don't change the orientation, where I do change the orientation. And just like we had the capacity function and the control conditions, we give, for the most part, really low limited capacity. People are just pretty bad at doing those two dots together when they don't have the additional orientation. And this is also then accounting for the potentially differential accuracy in each of those conditions. Here it's a little hard to tell, but it's actually telling a similar story to what the capacity coefficients were telling before. There are some individuals that are super capacity, so that orientation cue helped them to be even better than the independent parallel baseline. But for the most part, the mass of the group is down below that, so you do still get a limited assessment value at the group level. Nonetheless, you definitely get better performance at the group level and comparing individuals within subject. Colors may or may not match. Sorry about that. But even when looking at it within subjects or at group level, it's definitely better performance when you have that orientation. This had very high accuracy, so these lines look almost exactly the same as the lines I showed you before for the capacity coefficient. When you have the aligned faces, people are almost across the board, super capacity, so better with the pieces together in common orientation than they are with the parts. And at the split level, we got some better, some worse. At the group level, it's just a little bit above baseline value. But again, superior performance in the configured condition. So when they're in their canonical orientation, better than parts alone, but also better than the misaligned condition. I don't have in the R package the assessment functions coded up for 4 different sources of information. So I can't show you the same functions for the words. But because the accuracy was fairly high, it wouldn't change very much. So again, for these data, they were high accuracy. The assessment functions don't change very much. But when you get into data sets where you're going to have much lower accuracy, these will be really valuable. It kind of gives you the same idea as comparison to a baseline model and allows you to compare across the conditions. All right, so basically what I just said there, the capacity assessment function can be used with a wide range of stimuli. It's a model-based baseline. templates are estimated from performance that allows for direct comparison between configurations of same or different parts. So again, we can compare configurations of consonants to configurations of letters that make up standard hyphen we've demonstrated their use in 3 different types of configural superiority tasks: the face superiority, word superiority, and objects or something superior, dot superiority, I guess. So they're fairly powerful, diverse functions. So that's it for the content of the talk. This is my messy slide here, highlighting the fact that a lot of this work has been in collaboration with Jim. In fact, I think his name is on every relative citation up here. The particular experimental data we have are highlighted here. So the face superiority effect, this is work that Devin Burns did. The dot stuff was work with Robert Hawkins and Ani Adels, and the word superiority work done with Chris Tompkins. And there's a mass of theoretical papers and classical coefficient. So thank you very much.
Thank you, Professor Houpt. Any questions?
I'm wondering, if you look at individual difference in the sense that people are doing across the tasks, and to see that we're consistently showing the same kind of sort of performance.
Yeah. So the word data we had, this is before we had the statistics, so we just collected a lot of data because we didn't know how to statistically test. So this is actually 2 days worth of data for each of these that had 10 days total of testing on them. And there was a little bit of variability within subject on day 1 versus day 2 in each of these conditions. Even a little bit in the ordering. So some participants might have been better on the pronounceable non-word on day 1 than word, and then on day 2 been better with word than pseudo-word. But there weren't any consistent patterns in those individual differences across there. It did actually inspire, so we picked up the same basic task and tried to use it to examine dyslexic populations. So we took a subset. I think we took the word, pronounceable non-word, and I think the only one we dropped out was the upside down condition. Wondering that if we'd see, say, word maybe drop down to baseline, pronounceable non-words drop down to the baseline performance, or maybe even as bad as the unfamiliar characters of the dyslexic population. And we also took a bunch of different reading measures. Surprisingly, a number of our dyslexic participants actually were equal in performance on the word and pseudo-word to the control individuals, and their unfamiliar character capacity coefficients were actually up higher, so they looked more like words and pseudo-words. So somehow they were potentially using some alternative mechanism that allowed them to perform better with these unfamiliar characters than the standard control.
So I'm also curious whether you test subject across the dots, the faces, and you see some consistent pattern.
Yeah, that's a great question. So I haven't done that intentionally. There might be some people mixed in here who've done that. But I think Ching Don, some of his students, have looked at people across various tasks using these measures. So if we people to talk to.
We have 3 more minutes. Any questions? If I can just follow up, what do you think happened
Was the basic thing, that's the thing I'm so interested. Why is it, for some individuals that can still sort of command the super capacity with the misalignment, that's sort of how common it is. I would say.
I don't know. This is where I default to the face perception experts to come up with hypotheses on what that might be. So it might have been that this misalignment just wasn't a strong enough cue to disrupt all of the configurality. Kind of stabbing at answers here. Jim, do you have a potential answer? I'd be happy to get some help.
Well, yeah, I think looking at it from a positive point of view, it's suggesting that the dichotomy of configural versus non-configural with a shift like that may not be correct. Maybe there's a continuum, just as you might lose the configurality as you slowly rotate at pace. This might be more like that.
Thank you again. Oh, yeah. One more question, sorry. Can't cut off those.
As we know, LBA capacity is related to additional SFT capacity for the efficient functions. So how is it related to the assessment function?
The way I see it, and I'm not sure if Ami would see it different or Jim would see it, but the way I see it, the assessment function is really a non-parametric version of what they did with the LBA. So the LBA model, for those of you who aren't familiar with it, they took an information accumulator model and set up a baseline usage prediction using those parametric models. And then they compare the rate of processing in those models when you have the pieces in isolation, when you have the pieces together. So I'd say it's fairly closely related in sort of theory to these assessment functions. And what we're looking at as a usage prediction for correct and incorrect processes, we just take a more specific set of assumptions to use that LBA-based capacity measure. Whereas in the assessment function, we're really trying to get away from as many assumptions as possible. The trade-off rate, we get a mess like this. Not that the LBA equations are that easy, but a mess like this and the statistics are a little bit more difficult here.
All right, we have stopped here, and let's join the coffee break. Please come back in 10 minutes. Thank you.